peering through the infinite, how humanity saw the unseeable. For centuries, the night sky was a canvas of mystery. Our ancestors counted stars by the thousands. But today, we estimate there may be 100 billion stars in just our own Milky Way. Some argue the number could be twice that, or even more. And beyond it, at least 100 billion galaxies stretch across the observable universe, each holding secrets we've only begun to uncover. Our knowledge has exploded in just 100 years. What was once a single galaxy cosmos now spans endlessly in all directions, but we're still tethered by distance. Even Voyager 1, launched in 1977, is merely drifting through interstellar space, unable to ever reach another star system in our lifetimes. So instead, we study the cosmos through light, the ancient messengers that travel across time to reach our telescopes. On Earth, we built giants like the Keck twins in Hawaii, with segmented mirrors that constantly adjust against gravity's pull and atmospheric distortion. We crafted adaptive optics to rival space telescopes, guiding Earth-based instruments to breathtaking precision. We scaled mountains like Chile's arid Atacama Desert to find clearer skies and quieter light. Then we thought bigger. What if telescopes across the planet could unite, not just to look at stars, but to see the invisible? Black holes, once dismissed as math fiction, were proven real by their violent effect on nearby matter. At the centers of galaxies, we found supermassive beasts devouring gas and dust in glowing, swirling disks, firing jets of plasma at near light speed. But could we see one? That dream birthed the Event Horizon Telescope, a worldwide collaboration synchronizing instruments from Antarctica to Hawaii to form a planet-sized eye. No cables could connect them. Hard drives had to be flown across continents. More than 200 scientists, engineers, and theorists came together to chase a shadow, the silhouette of a black hole's event horizon. It was a feat of math, physics, and patience. Simulations were built, predictions made, and theories tested against bending light and warped space. In 2019, the unseeable was finally seen, the first image of a black hole, a glowing halo around a dark abyss. A human triumph made possible not by reaching the stars, but by listening to their ancient light. Through the eyes of Earth, how we photographed the invisible and found new worlds. It began with a mystery, strange, intense radiation pouring from the center of galaxy M87. The Hubble Space Telescope revealed a colossal jet of matter stretching light years into space. Something extraordinary was happening there, something unseen. In April 2017, a bold experiment unfolded. The Event Horizon Telescope, a network of synchronized observatories spanning the globe, turned its gaze toward that galactic heart. Each telescope was equipped with an atomic clock. Every millisecond of data had to align. Clear skies were needed at every site: Hawaii, Spain, Chile, Antarctica, and for a few precious nights conditions cooperated. What followed was a nerve-wracking silence. 5 petabytes of data, over 5,000 terabytes, were captured and shipped across oceans. South Pole data arrived months late. Only when everything was processed could they know. Did it work? In April 2019, the answer came. A glowing orange ring, the shadow of a black hole, 6.5 billion times the mass of our sun. Einstein's theory of general relativity, tested at its limits, held true. But the journey wasn't over. The EHT team now dreams of making not just images, but movies, mapping the spin of space-time itself. Meanwhile, in Chile, telescopes using infrared light peered into our own galaxy's core, where dust clouds conceal the stars' dance around a dark, invisible point. Over 16 years, astronomers tracked their orbits. One star, S2, whipped past at 3% the speed of light, its light shifting toward red just as Einstein predicted. Another triumph. But if black holes are our cosmic monsters, what about distant worlds that could host life? Enter the exoplanet hunters. Telescopes scan stars for flickers of dimming, signs of planets passing by. Others looked for gravitational wobbles in starlight. This search found thousands of planets, many giant like Jupiter, but some stood out. One, GJ667cc, is a rocky world 5 times Earth's mass, orbiting within its star's habitable zone. Another, the TRAPPIST-1 system, 40 light-years away, stunned astronomers. 7 Earth-sized planets, 3 in the habitable zone. A compact system orbiting a cool red dwarf, it's now a top target for future exploration. We don't yet know if these worlds hold water, air, or life, but our telescopes are evolving. Soon, we'll read the chemistry of alien atmospheres and search for signs of biology across light years. From photographing black holes to finding Earth-like worlds, we are witnessing a golden era of discovery. The universe is no longer distant. It's unfolding before us, one beam of light, one brilliant idea at a time. Eyes in the sky, dreams beyond Earth, the rise of a new space age. To find new worlds, we had to look differently, not just farther, but smarter. That's why NASA launched TESS, the Transiting Exoplanet Survey satellite, into a unique orbit tilted 40 degrees off the moon's path. Its mission, scan the skies, segment by segment, tracking subtle dips in starlight that might signal orbiting planets. It doesn't do this alone. When TESS spots a flicker, Earth-based telescopes rush to confirm it, marking a new era of collaboration between orbit and ground. Early in its mission, TESS confirmed dozens of exoplanets, with over 1,000 more flagged as candidates. One such clue led to Beta Pictoris, a young star just 20 million years old. Its strange light pattern wasn't from a planet, but from 3 comets, evidence of a still-forming planetary system. And the search is only expanding. Soon, W1st, now called the Nancy Grace Roman Space Telescope, will scan the sky using gravitational microlensing, where the gravity of one star bends the light of another, revealing hidden planets in the process. But W1st isn't just hunting exoplanets. It's probing deeper cosmic riddles, like why galaxies spin too fast to hold themselves together. The math says they should tear apart, yet they don't. The explanation? Dark matter, an invisible substance that doesn't shine, reflect, or react. It shapes the universe purely through gravity, and there's 5 times more of it than normal matter. But we've never seen it, not directly. And early galaxies, some more than 10 billion years old, rotate more slowly, suggesting dark matter's influence may have evolved. It's one of cosmology's great puzzles. At the same time, space exploration is shifting. NASA's new Orion capsule, launched aboard the Space Launch System, is set to return humans to the moon. But low Earth orbit, that's becoming commercial territory. SpaceX and Boeing are leading the charge, ferrying cargo, and now astronauts, to the International Space Station. SpaceX's Crew Dragon is a sleek evolution of its earlier designs. Boeing's Starliner, capable of reusing and landing on dry land, aims to cut costs and increase turnaround. Both use capsule-mounted launch escape systems, a modern take on the classic ejector seat. Starliner's 2019 uncrewed test flight fell short of reaching the ISS due to a timing error, but valuable data was recovered. The redundancy, 2 completely separate systems, ensures NASA won't be grounded again as it was after the shuttle disasters. While government missions reach for the Moon and Mars, private companies like Virgin Galactic chase suborbital tourism. The line between science fiction and reality grows thinner each year. From finding exoplanets orbiting distant stars to preparing for commercial space flights, a new space age is unfolding. It's not just about reaching farther, it's about knowing more, about where we are, where we come from, and what worlds might wait beyond the sky. Return to deep space. The rise of next-gen spacecraft and the new moon race. When SpaceX unveiled the original Dragon capsule in 2010, its heat shield quietly hinted at the company's bigger ambitions. Unlike other ISS cargo craft, Dragon could survive re-entry. It even had a window, and that wasn't just for show. In 2014, with NASA's contract for a human-rated spacecraft in hand, SpaceX began work on Dragon 2, refined, reimagined, and ready to carry astronauts. Its solar-powered service module eliminated the need for clunky deployable wings. Inside, sleek touchscreens replaced traditional controls. The Dragon 2 could carry 7 crew members, though NASA planned for 4 at a time. By March 2019, the uncrewed Demo 1 mission launched flawlessly, docked with the ISS, and returned to Earth, safely, smoothly, and without incident. Confidence was high, but spaceflight is never simple. During a ground test, a leaky valve caused an explosion, delaying further tests. Still, the in-flight abort test in early 2020 was a success, proving the capsule could eject and protect its crew in a worst-case scenario. As the Dragon moved closer to crewed flights, another contender remained in the shadows. Dream Chaser, a lifting body spaceplane from Sierra Nevada Corporation. Though originally passed over for not meeting NASA's crewed mission deadlines, Dream Chaser gained traction with a cargo contract. Its reusable design could glide to a runway landing, avoiding ocean recovery costs. With interest from ESA and new, less toxic fuel systems, Dream Chaser is still in the race, quietly preparing for a future where lifting bodies could return astronauts like airplanes. Meanwhile, NASA shifted its exploration gaze beyond Earth orbit. The Artemis program aims to return humans to the Moon using the Orion spacecraft and the powerful Space Launch System, SLS. Orion, built for missions up to 21 days with 4 astronauts, features ESA's advanced service module, recycling water, and providing solar-powered life support. Its abort system, launch-ready at the capsule's tip, is built for speed and safety. The SLS rocket, a blend of shuttle-era heritage and modern innovation, uses 4 upgraded RS-25 engines and 2 massive solid-fuel boosters. In its initial Block 1 configuration, it will send an uncrewed Orion around the Moon. Later versions will fly farther and heavier payloads, including modular habitats and landers. Despite delays, test flights have proven successful, from high-orbit re-entry tests to upper-stage trials with the interim cryogenic propulsion stage. While private firms race to own low Earth orbit, with Boeing's Starliner and SpaceX's Crew Dragon, NASA is once again aiming higher, toward the Moon, toward Mars, toward the unknown. The Dragon, Dream Chaser, Starliner, and Orion aren't just spacecraft. They're the vessels of a new era, and each mission, each launch, is a step closer to humanity's return to deep space. From fire to fusion, humanity's return to the Moon and the origins of Earth. In a world rediscovering its passion for the stars, a new chapter is being written. The Artemis program, NASA's bold pledge to return American astronauts to the Moon, accelerated after a striking declaration in 2019 to land by 2024, years earlier than planned. The SLS core stage, towering and powerful, was shipped to Mississippi for a rigorous Green Run test campaign, marking the beginning of a long-awaited era. Parallel efforts see commercial partners preparing lunar landers and a moon-orbiting space station, the Gateway. While timelines tighten and budgets waver, Artemis remains steadfast, with Artemis 1 launching uncrewed into deep lunar loops, and Artemis 2 preparing to carry astronauts farther than any human has gone in 50 years. The first crewed landing, Artemis 3, will send a man and a woman to the Moon's shadowed South Pole, where ice waits in the darkness, vital for life and fuel. But while we chase the Moon, we look back to our cosmic beginnings. The Orion Nebula, a vast stellar nursery, shows us how stars are born and planets take shape. Within its swirling dust, protoplanetary disks formed new solar systems, just as ours did 4.6 billion years ago. Jupiter, the first to form, played gravitational gatekeeper, reshaping the fates of early planets. Earth's destiny was sealed in fire and violence, colliding with a Mars-sized body that gave birth to our moon and set the stage for life. This moon, though modest in size, stabilized our planet's axis and climate, allowing life to flourish. Asteroids and comets rained water onto Earth in a cataclysmic bombardment, and beneath this chaos, our planet found calm. Magnetic fields deflected radiation, oceans flowed, and 2.7 billion years ago, oxygen filled the skies. Now, as new spacecraft are tested, Virgin Galactic's Unity for tourists, Launcher One for satellites, and Cosmic Girl missions from modified 747s, the future of exploration burns brightly, and in that light, we are reminded that Earth is not just our home, it is a miracle, a product of destruction, gravity, and chance. And with each mission, each rocket, each orbit, we draw one step closer to understanding how rare, how precious, and how extraordinary that truly is. Signals in the sky, how satellites, science, and a silent gas warned a warming world. It began with the simplest of life, plants, quietly inhaling carbon dioxide and exhaling oxygen, unknowingly transforming the atmosphere and cooling the earth. This oxygen, once a waste product, would later become essential to animals, ecosystems, and every breath we take. Yet the changes it sparked weren't all gentle. As insulating gases vanished, the earth cooled, entering cycles of ice ages and brief, warm reprieves, cycles revealed in ancient layers of ice trapped deep in the Antarctic and Greenland. Within those frozen time capsules, tiny air bubbles whisper the story of Earth's ancient climates, carbon dioxide rising with warmth, falling with ice. But are we warming because of CO2, or is CO2 rising because of warming? That question drove scientists like Charles Keeling, who in 1958 began measuring CO2 from Hawaii's Mauna Loa Observatory. His Keeling curve soon exposed a troubling trend: steady seasonal rises in CO2, unshaken by weather or ocean currents. Meanwhile, space technology raced forward. With the launch of Tyros in 1960, humans could observe cloud patterns from orbit. Later, the Nimbus program expanded this view, capturing atmospheric, oceanic, and polar data, though the earliest images were stored on film reels, not servers. A new understanding emerged. Earth was a complex, interwoven system. Melting ice affected ocean currents, which shaped weather patterns, which in turn fed or starved entire regions. Polar ice and cloud cover, key to reflecting sunlight, were thinning. Vegetation too played a role, pumping water vapor into the sky and balancing the carbon equation. But humanity, growing from 3.5 billion to over 7.7 billion in just 50 years, began to tip that balance. Satellites revealed shrinking forests, expanding cities, and darkening ice sheets. And still, scientists hesitated. Was this natural variation or something more? Then, in the 1980s, the sky itself betrayed the truth. Spectroscopy exposed a gaping hole in the ozone layer above Antarctica, not caused by nature, but by human-made chemicals, CFCs. Each chlorine atom released into the stratosphere could destroy over 100,000 ozone molecules. It was an invisible crisis, spotted only because science had learned to look. The world responded. The United Nations launched global talks, industry shifted, and the ozone hole began to heal. This moment became a warning. Humanity, through sheer scale, could alter the planet's protective systems, but with awareness, we could also begin to repair them. Today, the lesson lingers above us like the sky itself, quiet, vast, and fragile. And the melting silence, how a warming Earth sends warnings we can no longer ignore. In 1989, The Montreal Protocol marked a rare moment of global unity, every nation agreeing to phase out ozone-eating CFCs in a bid to protect Earth's atmosphere. It worked. But by then, another, more insidious signal had already begun to rise: global temperatures. Across the icy poles, the planet's frozen reservoirs, Antarctica in the south, Greenland in the north, and the ever-shifting sea ice in between, began to show signs of retreat. NASA's GRACE satellites confirmed what climate models had feared. Ice was vanishing fast. Greenland alone shed over 280 gigatons of ice annually, while Antarctica lost more than 130. Since 2005, this melt, coupled with expanding seawater, has pushed sea levels up nearly 4 centimeters. Precision satellites like Jason 3 revealed an unsettling truth. The ocean isn't rising evenly. Red zones spike near coastlines, blue ones signal regional dips, all shaped by currents, seabed topography, and the Earth's spin. In places like the Camargue region of southern France, the sea has reclaimed hundreds of meters of land, pushing back seawalls and shaking communities. But the damage doesn't stop at the shore. Oceans, now 93% warmer due to trapped greenhouse gases, fuel stronger storms. Argo floats detect warming waters, and meteorologists see the result: long-standing records shattered, hurricanes intensifying, droughts stretching on. Satellites from NASA and ESA chart CO2-like weather, visualizing the pulsing breaths of carbon from cities and wildfires alike. Copernicus's Sentinel satellites offer live data, freely accessible, showing a planet in flux. ESA Director Joseph Aschbacher points to graphs tracking CO2 over 800,000 years. Never in that time had it breached 300 parts per million until now. We're well past 400. Meanwhile, global summits like COP25 stall in negotiation. The Earth is still bleeding heat. From the ozone layer to rising seas, the atmosphere to ocean depths, satellites whisper a warning across frequencies and wavelengths. And like Sputnik's first beeps, dismissed by some, decoded by few, today's signals urge action. Earth is our only home. Its fragile balance is not just a matter of science, it's a responsibility. A thousand eyes in the sky, the silent race to own Earth's orbit. In 1959, on the shores of Crimea, Soviet engineers began welding warship remnants into what would become the Pluton receiver, a crude, ingenious listening post made from submarine hulls, railway bridges, and battleship turrets. It was a symbol of Cold War creativity, and it stayed active until 1978. As satellites evolved, so did the complexity of communication. Low Earth orbit demanded nimble, fast-tracking antennas, while deep space probes required massive dishes with unwavering precision. In the US, AT&T's Telstar made history in 1962, relaying live television across the Atlantic. Briefly, its low orbit meant fleeting availability, and nuclear tests in space cut its life short. The Cold War's unintended consequences ignited a new treaty, banning atmospheric tests and paving the way for safer satellite development. Then came geostationary orbit, where Early Bird, or Intelsat 1, revolutionized communication by hovering in sync with Earth's rotation. It could beam TV or handle 240 phone calls, a modest start to what would become a multi-trillion-dollar industry. Today, over 240 geosynchronous satellites orbit silently above the equator, relaying data, weather reports, and military intelligence. NASA's TDRS fleet and ESA's laser-based EDRS relay systems offer near-instant data transmission, some at 30 times the speed of traditional radio waves. Polar orbits, like those used by Europe's Copernicus Sentinel satellites, map the entire planet daily, feeding real-time climate data into global systems. But all this activity comes at a cost: a growing cloud of space junk. With over 1,900 operational satellites and tens of thousands of debris fragments, collisions are a constant threat. That threat grows daily, SpaceX alone plans to launch over 12,000 Starlink satellites, building a mesh of broadband connectivity across Earth. These small, mass-produced craft use krypton-fueled thrusters, phased array antennas, and stack like dinner plates inside Falcon 9 rockets. Once deployed, they scatter like seeds, spreading into orbital formation. By 2024, Starlink will outnumber all previous satellite systems combined, dwarfing even Iridium's once revolutionary 66 satellite grid. But astronomers warn of a crowded sky, where twinkling stars may soon compete with broadband constellations, and yet latency, the time it takes data to travel, is Starlink's secret weapon. For stock markets and remote communities alike, microseconds matter. Other tech giants like Amazon and OneWeb are racing to catch up, but SpaceX, with its own rockets, satellites, and even reusable fairings, holds the edge. From crude antennas made of scrap metal to lasers pulsing silently between orbiting platforms, the sky above us is no longer just a realm of stars. It's becoming a battlefield of information, silent, crowded, and rapidly changing. Whispers from the edge, telescopes, satellites, and the cosmic balancing act. As more satellites take to the skies, astronomers are beginning to sound the alarm. Survey telescopes that rely on long exposures to capture rare cosmic events, asteroid flybys, supernovae, distant quasars, are now contending with streaks of reflected light from Starlink satellites that cut across the night sky like luminous scars. Simulations from the massive Synoptic Survey telescope, nestled in the Chilean Andes, suggest that in the coming years, entire swaths of critical observing time will be rendered useless. It's an ironic tension, advancing technology helping humanity stay connected while simultaneously clouding our ability to look outward. Starlink, though ambitious, remains uncertain. Past ventures like Teledesic and Skybridge collapsed under financial strain. Elon Musk himself admits it could fail. Meanwhile, communications with deep space probes continue under far different constraints. NASA's New Horizons, launched in 2006, reached Pluto after nearly a decade, its 8 gigabytes of precious data taking 16 months to trickle back to Earth at mere kilobits per second. Voyager 1, humanity's furthest emissary, now whispers home at just 160 bits per second, slower than Morse code. But perhaps no tool has reshaped our cosmic understanding more profoundly than the Hubble Space Telescope. From Galileo's first glance at the moon to Newton's reflecting telescope, each leap in optics pulled Earth further from the center of the universe. In 1990, after years of delays and a dramatic launch aboard the Space Shuttle Discovery, Hubble took its place above Earth's distorting atmosphere, only to reveal its primary mirror was flawed. A rescue mission in 1993, executed through a ballet of 5 spacewalks, corrected its vision. What followed was a torrent of revelations. Black holes anchoring galaxies, galaxies stretching back in time, the cosmic expansion laid bare. One of Hubble's early triumphs was documenting the dramatic crash of comet Shoemaker-Levy 9 into Jupiter in 1994, giant scars larger than Earth marking the gas giant's surface for weeks. Spectral analysis revealed compounds never before detected at Jupiter, painting a vivid picture of solar system violence. But today, even Hubble's majestic gaze is threatened, not by funding or technology, but by the ever-thickening veil of satellites orbiting below. As telescopes aim deeper into space and probes push further outward, a new kind of celestial traffic jam is emerging, forcing us to reconsider what we might be losing in the race to connect, while we try to understand the cosmos that first inspired us to look up. When the sky almost went dark, Hubble's near collapse and the legacy that followed. Just days before one of the most anticipated celestial collisions in history, the comet Shoemaker-Levy 9's impact with Jupiter, Hubble Space Telescope suddenly fell silent. It slipped into safe mode, ceasing all commands, refusing to point. and leaving astronomers fearing they'd lose the chance to witness the event. The problem traced back to a memory switch, recently installed but not fully mastered, and a counter that had simply run out of numbers. A quick fix saved the mission, but the scare exposed how much operators still had to learn about Hubble's intricate systems. Unlike traditional spacecraft, Hubble has no thrusters. Instead, it spins 4 heavy reaction wheels to pivot with surgical precision. With its guidance sensors locking onto bright stars and gyroscopes tracking every subtle movement, it could aim with breathtaking accuracy within 2 millionths of a degree. That precision allowed Hubble to perform its most daring feat in 1995, staring at a seemingly empty patch of sky for 10 straight days. What it revealed stunned scientists. Thousands of ancient galaxies, many 13 billion years old, crowding the darkness in a cosmic time-lapse known as the Deep Field. It was a glimpse into the infant universe, showing strange, chaotic galaxies, nothing like our own. But even as its discoveries captivated the world, Hubble was reaching the edge of its capabilities. Engineers designed upgrades, infrared sensors, solid-state memory, new guidance systems, and astronauts returned again and again to fit them during high-stakes servicing missions. In 1999, another near-fatal blow, 4 gyroscopes failed, sending Hubble once again into safe mode. The fix came quickly, but with the Columbia disaster in 2003, all future shuttle missions were grounded, including those planned for Hubble. That decision marked what many feared would be the telescope's quiet death. But the public loved Hubble. Its cosmic portraits, from the pillars of creation to ancient colliding galaxies, turned it into a scientific celebrity. Thanks to public pressure and political allies, a final mission was approved. In 2009, Atlantis carried out the most complex overhaul in Hubble's history. New instruments, batteries, gyros, and repairs to cameras never designed to be fixed in orbit. When it was released, it was better than ever. The stunning images that followed, from tightly packed star clusters to galactic collisions, proved that Hubble had entered a new golden age, but time catches up with all machines. By 2018, its last reserve gyroscopes began to fail. With delicate reboots and software workarounds, Hubble kept going, now relying on star trackers and clever engineering. Its death is inevitable, but its legacy is secure, and waiting in the wings, undergoing final preparations, is its heir, the James Webb Space Telescope, designed to peer even further, colder, and deeper into the unknown. Hubble changed the way we see the universe. Webb may change what we believe about it. Webb's watchful eye, unfolding the universe's secrets from a million miles away. It begins with a mirror, unlike any before it, composed of 18 golden hexagons, folded carefully like origami for launch. The James Webb Space Telescope, a marvel of modern engineering, was born not just from NASA's ambition, but through the combined efforts of the European and Canadian space agencies. Though it dwarfs Hubble in size, Webb is lighter, more agile, and infinitely colder. Once deployed, it drifts into position at the second Sun-Earth Lagrange point, a gravitational balancing act 1.5 million kilometers from Earth's dark side, where day never breaks. There, shielded by a 5-layer sun shield the size of a tennis court, Webb cools to just 50 degrees above absolute zero, its mid-infrared instrument plunging further, chilling to a mere 7 Kelvin thanks to a helium-cooled cryocooler. These extreme conditions are not a flaw. They are the very feature that allows Webb to see what Hubble cannot: the ancient light of the earliest stars, the cradles of galaxies, and the atmospheres of distant exoplanets. It is designed to peer deeper into the cosmic past than ever before. Webb doesn't replace Hubble, it extends its legacy, rewinding the universe's story billions of years further, past the curtain of cosmic dust and into the untouched dawn of structure and light. as it unfurls in space, aligning its mirrors with laser precision and calibrating its sensors. Webb begins its long vigil, poised to capture the universe as it was, not just as it is. From the ashes of collapsed stars to the silent drift of alien worlds, every photon it receives is a whisper from a forgotten age, now heard at last. Touching the fire, Parker's daring descent into the heart of the sun. In the chill of a pre-dawn sky, a spacecraft named Parker prepared to do the unthinkable, fly into the atmosphere of the sun, not merely to orbit or observe from afar, but to plunge directly into the fiery corona, the outermost layer of our star, where temperatures soar into the millions and mysteries still rule. Built light but mighty, Parker Solar Probe weighed less than a small car, yet required one of the most powerful rockets on Earth, the Delta IV Heavy, to hurl it toward the furnace. Unlike any mission before, this was not just about surviving heat. It was about rewriting everything we thought we knew about solar physics. Armed with a carbon composite shield designed to endure over 1,500 degrees Kelvin, the probe would race at 720,000 kilometers per hour, fast enough to orbit the Earth 17 times in 1 hour while keeping its delicate instruments at room temperature behind its umbrella of protection. Named in honor of Eugene Parker, the man who first theorized the solar wind, the mission was more than symbolic. It was the first time NASA had named a spacecraft after a living scientist, and rightfully so. Over the years, Parker's elliptical trajectory would be sculpted by 7 slingshot passes of Venus, each bending its orbit closer to the sun's flaming surface. On board, instruments would awaken in silence, collecting data inside the solar atmosphere, while Earth waited in radio silence, trusting that the probe could survive its solo descent. With each pass, Parker dipped deeper, revealing hidden currents of plasma, tracing magnetic field lines, and capturing images of coronal structures no eye had ever seen. Early findings shocked scientists: particle streams more chaotic than predicted, reversals in the solar magnetic field, and waves of energy that defied long-held assumptions. Yet with every discovery, new questions emerged. Why is the sun's outer atmosphere far hotter than its surface? What truly powers the solar wind that sweeps across our solar system? As Parker continues its dive, narrower, faster, bolder, those answers are drawing near. But perhaps more importantly, Parker reminds us that even in an age of AI and automation, the most profound scientific revelations still come from daring to go where no machine and no mind has gone before.